Um, Good afternoon. First of all, I would like to thank Professor Tadwalji and Professor Chandrasekharji for inviting me to give this talk. So when I asked who are the audience, I think they said that there are some university professors and some researchers. So I made this talk very general. Instead of going into the details of very advanced, instead of going to the very advanced things, I made it to very general talk. So first, since morning you've been hearing about the atmospheric radars, particularly the clear air radars, mostly the ST-MST radars, and then their applications to middle atmosphere, lower atmosphere, middle atmosphere, and ionosphere. And then Dr. Batra has also introduced you to the latest developments and also the advances in the ionosphere, advanced research in the ionosphere. So what I'm going to do today is actually I'm going to cover the meteorological aspects of the radar. So what is the textbook definition? Actually, if you say that meteorology, radar meteorology is a study of atmospheric science where you measure, the temperature, moisture, then the variations in the winds, rainfall, basically to understand the precipitation, thunderstorms, tornadoes, cyclones. So all these processes. So since we are using it as a radar to understand this process, we call it as radar meteorology. So this is the outline of my presentation. So first I'm going to talk about the various atmospheric radars that we are using for sensing atmospheric, to understand the atmospheric process and to monitor the atmosphere and meteorological process. Then I was also asked to talk about wind profilers a bit, because since morning we have been hearing about clear air radar. So I will just very briefly tell about what meteorological aspects that we can study with wind profilers. Okay, and then actually the radar meteorology, people traditionally the people talk about the Doppler weather radar. So the meteorological aspects using the Doppler weather radar. So I will spend quite a bit of time on the Doppler weather radars, particularly what are the how it operates, and then what are the modes of operation, and then what are the parameters that you get, and what for you are using, what for we are using these Doppler weather radars. And then what are the error sources in the normal single polarization Doppler weather radars. Then how we overcome those limitations with the introduction of the polarimetric radars. And then also, if time permits, I will just show some videos about the spaceborne radars that what we have presently. And then I will end my presentation by telling some challenges, and then way forward, which direction the community is moving. So these are the class of atmospheric radars, starting from the VHF frequencies to millimeter wave frequencies. You can see this is 30 megahertz to 1000 mega, okay, 1.3 and 1.4. Presently, people are operating at that frequency. So these radars, basically, people are using these radars for wind profiling applications. So since morning, you are hearing about these type of radars, where the main scattering mechanism is a Bragg scattering mechanism. So Bragg scattering, Fresnel reflection, and Fresnel scattering. So these radars basically get echoes from the changes in the refractive index field, and then so that we can use it to get the profiles of winds, particularly in the lower atmosphere, and then also the profiles of turbulence. So basically, it is used to get the wind field, and also to understand the turbulent process, and also obviously for atmospheric applications. So this, because it is continuously we get the wind profile, so we can study the waves and associated dynamics. So this radar basically, these radars operating in this frequency band is called clear air radars or ST-MST radars or wind profilers. So actually traditionally the Doppler weather radars, they operate at these three frequency bands, S band, C band and X band. The corresponding frequencies are given here. So they are traditionally used for Doppler weather, these weather applications. So they basically use it to study the, to track the storms, to get the three-dimensional precipitation, to get the vertical structure of precipitation. So for these kind of things, we use these radars. Of course, depending on their the location and then their end use, they choose the frequency. Whether those who want a long range data, so they will go to the S band or C band, and the people who want actually to study the light precipitation, and then they wanted to understand the thunderstorm and associated phenomena, and then also those who are in the mountainous terrain and then the cities. So because of the so many blockages will be there, so they will go to the X band. So depending on the application, people choose the frequency. And then there's another class of radar is called cloud radars. So they operate at very high frequency. That's they operate at the Ka band, either Ka band or W band. So basically they are used to study the clouds, cloud microphysics, cloud process, and then the very light precipitation. Because the attenuation is very high at these frequencies, so they cannot be used. We cannot use them for the for rainfall, for precipitation studies. So coming back to the wind profiler, so I'll spend some time on wind profilers and then how we are using it for meteorological applications. The wind profilers actually operate in three frequency bands. Traditionally, they are operating at three frequency bands. One is around 50 megahertz. So they are called MST radars. So they operate around, they use huge antennas, and then the regularity size is 3 meters. So they basically to study the mesosphere, stratosphere, and troposphere, and then wave dynamics, middle atmospheric dynamics, and for those applications we use these radars. And there is another type of radars actually called ST radars. They operate at 400 megahertz. So in the US they have a big network of 400 megahertz radars. So it was one time actually once it was very popular, 400 megahertz radars. Then another class of radars actually is operates at L band frequency, is either at 1.3, 1.2 gigahertz frequencies. So they are basically a small radars, basically for the wind profiling applications in the boundary layer. So they provide, they're actually, some countries have a network of these wind profiling radars, small radars. So depending on your application and in your region of interest, you can choose the frequency. If you want the mesosphere, stratosphere, troposphere, all three regions, if you want to probe, then you can go to the MST type, 50 megahertz, and then if you're interested only up to 10 kilometers or so, then you can go to 400 megahertz. Then if you're interested only in the boundary layer, then you can choose a 1.3 or around 1 gigahertz. There is now actually recently there is another class of radars have come. Actually, they are available only in India. It's a 200 megahertz, and then in India we have presently three such radars available in India. One in Cochin, and the other one in Aries, and one more in the northeast. So why I'm telling all these frequencies is because since morning you have been hearing about the Bragg scattering, that is basically the changes in the refractive index. They will cause the radio wave to backscatter. There is another, this is actually the clear air scattering. Similarly, there are particle scatterings are also available. So in the atmosphere, there are so many particles. You have cloud particles, rain particles, precipitation particles, rain, snow, aerosol particles, all particles are there. So similarly, there's also when a radio wave propagates, it will also undergo a particle scattering. So one such, so these radars, particularly this Rayleigh scattering, this particle scattering is frequency dependent. It depends frequency. You can see these lambda to the power of 4. It is in the denominator. If the wavelength is small, then you will get a very strong Rayleigh backscatter. So when you use a VHF to UHF radars at these frequencies, particularly at VHF radar, you get a very strong backscatter because of the Bragg scattering, but also you also get a weak, very weak backscatter due to the particles when rain is there. So you will also get a backscatter from the rain particles. But as the frequency increases, if you go to the UHF frequencies, then you can see, because the lambda is very small, so you will get a very strong backscatter, Rayleigh backscatter at UHF frequencies. So on the left side of the figure, you can see this is UHF radar. You can see a very strong backscatter from the rain. Whereas at VHF frequencies, you see two echoes. One echo is coming from because of the Bragg scattering, other echo is coming from the Rayleigh scatter. So, wind profilers can also be used to study. The figure clearly indicates that wind profilers can be used to study the precipitation. So then, particularly when you're talking about the VHF radar, then you have two echoes. So the problem from the beginning is how to segregate these two echoes, how to identify automatically these two echoes, which one is what. Is it a Bragg scatter or is it a Rayleigh scatter? If you don't correct these things, then what is the error it will give in your estimates? All these things people have been studying from the beginning, and then recently also there are several automatic methods are actually given in the literature. Something like in Williams actually has done a dual frequency method. He has used two radars. One radar which is more sensitive to precipitation, other radar is sensitive to both clear air and precipitation, like VHF radars. So then he will use the echo from the precipitation from the high frequency radar, and then he will suppress that portion in the VHF radar. So using that technique, he has removed the precipitation component, and then he has got the clear air moments. But at all the places, actually, we don't have this two radars. So only at few places you will maybe be having two radars. So then we devised another method called symmetric method, where with one radar itself we can segregate these two, and then we can get the moments. So the why we have to do, actually, if you see the morning, I think Professor P.B. Rao actually has explained you that what are the three basic moments that you can get with wind profiler. Is actually, one is the backscattered power, other one is the Doppler velocity, third one is the spectral width. These are the three basic parameters you can get with the radar. So what they correspond? Actually, in case of a clear air, the backscattered power and then the spectral width, we can relate it to the turbulence intensity, and then we can also relate it to the stability of the atmosphere. And then the mean Doppler velocity, that we can use it to get the three-dimensional wind field. Pardon? I'm able to see full screen. So are you able to see my full screen?
Yes, hello? Yes.
Yeah, but then there is a complaint from NARL, our own people, that they're not able to see the full screen. That's why I'm asking.
No, it is a full screen for your present slide, and another one is your next slide. That's it.
It's a presenter view.
It's going good. Let's go, sir.
No,
please go.
Because some people.
Yes, sir. On their hider that click on that three dots.
Yeah.
Hide the presenter view.
Is it okay now?
Yeah, it's now in the full screen.
Okay. Yeah, okay. So the moments, actually, as I said, that the clear air, the backscattered echo, whatever you are getting, the moments that we obtain from the backscattered echo can be related to the turbulence intensity, and also from the Doppler we can get the three-dimensional wind field. Similarly, from the moments whatever you get from the precipitation echo, that we can relate, the backscattered power can be related. If you can calibrate the radar, you can relate it to the you can get the reflectivity factor, and then you can relate it to the rain rate. And also you can use this information to classify what type of precipitating system it is. Is it a stratiform rain? Is it a convective rain? Does it have any radar brideband? Something like that. So we can classify what type of precipitation it is using the backscattered power. Similarly, we can use the mean Doppler velocity from the precipitation particle. If you can correct for the clear air, then we can directly relate that to the fall velocity of the hydrometeors. So if it's a rain, then we can say that this is the rain is falling with this much velocity, fall velocity. And then in fact that we can convert that using the spectral width information, we can get the turbulence, and also we can convert the spectral width information, the spectra, to the raindrop size distribution. So the microphysical information of what you can get with this kind of radars. So I will show you one example of these things. So the most important the contribution that these radars have done is actually they have measured the intensity of the convection in terms of vertical velocity. So this is probably the only instrument which gives the vertical profiles of vertical velocity inside the clouds. Again, we are hearing some noise.
This is Harish. This is Harish who is talking.
If my voice is louder than his voice, then probably I will go ahead.
Sir, if they started the mic mistakenly, you can, I guess, mute them. You have that.
I think I don't have the.
Harish Singh. Okay. I'm removing him. I'm removing him.
Okay. So one of the biggest contribution that these radars have done actually in terms of in meteorology is actually it has given it directly measures the vertical wind inside the cloud and inside the cloud particularly. So you can see in different types of convection, within the shallow convection or deep convection or decaying convection, then you can see how the vertical wind is changing within the convective cloud, because this is probably this is the only instrument which gives that information very accurately. In other, even with the Doppler weather radars also we can get that information, but this is a kind of a derived product, but then this is a direct measurement. So we can study several things with this kind of information. Yeah, in fact, when we got this information, then we were interested to check whether the models are able to reproduce such vertical wind. And then when we compared with the model outputs with the different parameterizations we have tried, and then also explicit parameterization we tried, but we never got such a magnitude in the model. So models were able to reproduce only the time and then the vertical extent correctly, but then the magnitude, there is an order of magnitude difference is there between the models and then the actual observations. So these radars actually, they're very useful in providing the vertical wind, so they will become a benchmark for model evaluation. And also, as I said earlier, that we can use this information, but particularly if you have a UHF wind profiler, because we get a very strong echo from the precipitation. So we can use that information to study or to segregate different types of precipitation. whether it is a stratiform precipitation. We can see a clear radar breadband is present here, which is a signature of the stratiform rain. And then when you see here, very strong rainfall extending up to 8 to 10 kilometers, that is the region where the strong convection is present. So we can segregate the different types of precipitation using this type of radars. So another important contribution this radar has made is it is possible to get the raindrop size distribution. So raindrop size distribution is the fundamental property of the precipitation. So once we get that information, then we can calculate all the parameters related to the rainfall. So here you can see clearly that with using the dual frequency technique, some time back we have derived the raindrop size distribution, profile of raindrop sizes, and we can see here in this picture vertically how the raindrops are varying. As the raindrop falls down, so different size drops, how many the number density of the each size, actually they are getting reduced because of the evaporation. So we can get indirectly the microphysical information from the vertical variation of the raindrop size distribution, whether what kind of microphysical process is occurring there. Is it aggregation? The drops are colliding and then aggregating, coalescence is happening, collision coalescence is happening, so the sizes is increasing, or the size is decreasing because of evaporation or because of breakup. So like these these microphysical processes that we can get by measuring, by retrieving the raindrop size distribution at different altitudes. So this is another important contribution this radar has made. So now we'll go back, I'll stop there about the wind profiler. Now we'll go back to the meteorological radar, so the Doppler weather radar. So I will start, actually morning I have changed this slide because Professor P.B. Rao sir actually has talked about the World War II. Then while telling the evolution of the radars, he said that James Watson Watt actually has developed the radars for tracking these the aeroplanes and other things. So I will start from there. So during the World War, actually when they were tracking this the enemy aircrafts, they were most of the time the radar operators they have seen some other echoes which were not aircrafts, the echoes are not from the aircraft. So they are there because of the weather, so the disturbed weather, so maybe because of cloud, rain and other things. So they used to filter them to know where is the aircraft. But later then the scientists actually used these radars to detect the precipitation. So after the World War, the scientists actually taken these radars, and then in fact these radars, I think that Sri Raghavan used to tell, actually they were donated to the scientists after the World War. These radars were donated to scientists, meteorologists. So they took these radars and then they started using these radars for studying the precipitation. So the first bunch of the meteorologists, radar meteorologists, were David Atlas, and then in US, and then Marshall and Douglas there in Canada. So they started these groups using the radars. So the Marshall, actually the student of Marshall is Palmer. I think their research is still popular. The Marshall and Palmer relation of the DSD is still popular in the radar meteorology field. So these people were using these radars, but then actually the first use of weather radar and television in the United States actually started in 1961. So a local reporter, he wanted to know what is the size of the storm. A storm, Hurricane Carla, when it was approaching Texas, he wants to know what is the size of the cyclone, the hurricane. So he went to the radar site, and then he wanted to see what is the size of the side hurricane. And then that actually he has forecasted on a television. And then because of that, there was such a big hurricane, and then even US, they evacuated so many people, and was the biggest rescue operation. People say till now, it saved so many lives. So that was the first successful utilization of the radar data, radar images. So since then, actually, weather radar has evolved on its own. It is now extensively used by the weather services, weather departments, and then also researchers, basically to understand and to make short-term forecasts of future position intensities of rain, hail, and other weather phenomena. And also these data is assimilated into the numerical models to give a better improved weather forecast. So now we will see actually what is the need for the scanning Doppler weather radars. So whatever radar I have described so far, the wind profiler is a vertically pointing system. So it provides information only when the system comes overhead. Then only we get the information about the metallurgical, whatever metallurgical process I described. But all the systems won't pass over the radar site. So we need actually a tracking system which can track, which can identify these systems and then track those systems. And also we wanted to get the three-dimensional distribution of rainfall, including the vertical structure, particularly the vertical structure. So for this purpose, actually we need a scanning weather radar. So which can actually completely make a complete 360-degree scanning, and then which provides the weather information around the radar site. So you can see here at the bottom, I have taken it from the Chennai IMD radar. So it clearly can see actually a cyclone which comes very close to the radar and then it moves in this direction. So see, you can see here the cyclone. We can see this kind of a small scale structures within the cyclone and then the movement of the cyclone. So you can track the cyclone and in which direction it is moving. So we can give a nowcasting, so that you can say improved nowcasting we can provide, and then with a better lead time for rescue operators to take the necessary measures. So, and then you can, in the right side, you can see the rainfall distribution around the radar site within 100-kilometer area. We get the rainfall, generally we get the rainfall information from a rain gauge, but that's a point measurement. You can imagine how many rain gauges are required to get this kind of distribution. And with just one radar does that job. See, this radar is also not very different from the other morning, whatever radars we have been hearing. We have a transmitter in a more simplified way. I'm not going into the complex diagrams. So a transmitter which increases the transmitting power, and then through a duplexer it gives to the antenna, and then antenna radiates into the atmosphere, and then once it interacts with the target, in this case the target is the rainfall. So when it interacts with the raindrop, then you get a backscatter from the raindrop, and then through duplexer you are connecting it to the receiver. And then you process the data, and then you display it on the screen. So these are the important components of the radar. You have a transmitter. So most of the traditional transmitters are magnetron, either klystron. Now these all solid state transmitters are also available now. So the problem with the magnetron is it's an oscillator. The stability is an issue. So people have derived because they wanted to get the Doppler information also. So they have derived different techniques to get the Doppler information, like Cohon, receive, and other techniques. The klystron is more stable, and so it's more popular for weather radars. But then recent radars, actually they have gone to the solid state transmitters. And then you have a modulator, then you have a master clock oscillator, master clock, which is very important, which controls all the timing signals. Then we have waveguide, because the power, actually we transmit everything through waveguides instead of the coaxial cables to avoid the losses. Then we have a duplexer here. It's a very important component, because during the transmission it has to connect transmitter to the antenna without leaking any power to the receiver, because the receiver front end will have a very sensitive devices, so it will spoil those devices. So duplexer plays an important role in connecting the transmitter to the antenna during the transmission, and then during the reception it has to connect the antenna to the receiver. So the signal, whatever the backscattered echo, whatever we get from the atmosphere, that has to be connected to the receiver during the reception. And then there are, of course, you process the data, and then you have several displays, the several modes of operation. You have ASCO, PPI, RHI. So I will show actually what are they. Once we send the pulse signal, once we send the pulse into the atmosphere with the microwave pulse into the atmosphere, we get the backscattered echo from the atmosphere, from the precipitation particles. You can traditionally people use two techniques to get the basic parameters with the Doppler weather radar. Either they use a pulse pair technique or the fast Fourier analysis to get the three components: the radial velocity, the spectral width, and then the radar reflectivity factor. So the basically what it means is actually when you send a pulse into the atmosphere, you get the backscattered echo. So the backscattered echo amplitude gives the power, return power, and then the phase, whatever is there, that phase gives the information about your Doppler velocity. So the amplitude depends again on the particle size, particle distribution, and then particle orientation within the radar resolution volume. So all these things will add up, and then it will get the amplitude. If the particle is big, then you will get a large amplitude or the stronger return. So and then that means you can directly relate. You can relate the whatever reflectivity you are getting from this to the rainfall rate, because it depends on the rainfall DSD, drop side distribution. So we can relate it to the rainfall rate. So this is how we get this information. And then of course the phase difference between the received pulse and then transmitted, which gives the radial velocity of the particle. So we will show here, I think if it works, then okay, it looks like it's working. So you send a transmitted pulse, and then you are getting a return from the precipitation particles, and then that you process either the pulse pair mode or FFT. So you can get, and then the amplitude, you will get the received power, and that received power, if you put it in this equation, you will get the reflectivity factor Z. So all these parameters are radar related parameters, they're all constants. So you can make them as constant C here. And then what is the variable is only the range. Range is from the radar to the target, that range, and then the received power. So with that, you can calculate the reflectivity at different ranges. Similarly, you can get the velocity. So if you can make a complete 360-degree rotation, then you can get the distribution around you. So this is the different modes of scanning. This is with our X-band radar at NARL. So there are different modes of scanning. You can do scanning in different modes. You fix an elevation, and then you can make a 360-degree azimuth rotation, so they get a PPI. So this is how it looks like. Actually, this is the power and then reflectivity for two polarizations, but you can see one picture that is sufficient. So you can see this is the reflectivity around the radar. You can clearly see the rainfall around this region. There is, but then if you know that instead of completely rotating and then getting this information, if you know that precipitation is only in one direction, and you want to know you want to study the structure of vertical structure of that precipitation, that storm, then instead of making a big rotation, what you can do is you can point in that direction, so that azimuth you can fix, and then you can make an elevation map. So what you get is the height versus range, and then the reflectivity. So this is how it looks like, so that you can get the vertical structure of precipitation. You can see here, this is the range, and this is the height, and then this is the vertical structure. You can get this vertical structure, but if you are interested only in the vertical structure, you can make a RHA map. And then if you are interested only in some sector, you can choose the sector. I want only azimuth from 0 to 90 degrees, so you can scan in that mode also. But traditionally people use this kind of volume scan. So they make at one elevation, one azimuth, complete azimuth, and then go to the next elevation, and then make a complete 360-degree azimuth rotation, and then go to the next. So like that, they'll make some 10 to 15 depending on their interest, so that you will get you can create a three-dimensional distribution of precipitation. But whole volumes can takes about 5 to 10 minutes depending on your the number of elevations you are using, and then the rotation speed of the your servo system, your antenna. So this slide I have borrowed from IMD people, Dr. Suresh, just to show, because I cannot show all the results here. I'm just only listing what we can do with once we have a DWR for this kind of information, like three-dimensional distribution of precipitation and three-dimensional distribution of the Doppler velocity and spectral width. So what we can study. So there's a big list is there. We can get 100, 120 kilometer region. Within that area, you can get the precipitation rate. You can calculate wind shear and turbulence within that 100 kilometer range. And then you can also identify the wind discontinuity lines, horizontal divergence field, gust fans, microbursts. That's why they are mostly these close to the airports. Actually, you have these kind of radars. So it's very, very important for the aviation purpose. Then genesis of convective storms, the track and movement of storms, because we have seen one example, one cyclone, the movement of the storm. And also we can get the vertical profile of horizontal wind by using different techniques, because this is the radial velocity that what we get with the radar directly, but we can derive the vertical profile of horizontal wind using either VAD technique or VVAP technique. So few things we have to remember when you are talking about the Doppler weather radars, because you are sending the beam horizontally into the atmosphere. So and you know that the density decreases with altitude, and so when the beam passes from the denser medium to rarer medium, because density generally decreases with altitude, the radar beam is refracted, generally is refracted towards the surface of the earth. So there will be a normal refraction. Normally, the ray will undergo, but in all the calculations we take it as a normal refraction. But then in sometimes when the density decreases actually more than normal, then the beam bends less than the normal. So we get a sub-refraction. So then what happens is, you can see in the right side picture, the beam might overshoot the target and miss the precipitation. And similarly, sometimes it is when the decrease in density with height is less than the normal, the beam actually bends more than the normal, and then you get a super refraction. So it bends more, so it undershoots the target. And sometimes the ducting can happen, and then the wave will propagate over long distance, something like 1,000 kilometers also sometimes it will propagate. So we get the anomalous propagation and then false echoes. So, but then they can be identified in the radar images, so they can be removed. But sometimes we do get these kind of echoes. And then other things we have to remember is actually Earth is not flat. Earth is curved. So you have a curvature. We have to consider the Earth's curvature also into the picture when you are talking about the radars. Even if you point parallelly with the 0 degree elevation, because of the Earth's curvature, at different distances, the height of the your beam will be different. See, for example, at 50 kilometer, it may be around 0.3 kilometer, but at 100 kilometer, it is already, we are even at 0 elevation, you will be around 0.9 kilometer above the ground. And at 200 kilometer, you are 3 kilometer above the ground. So we need to correct these things while calculating if you want to get the height profile of the precipitation. And then this morning, I think Professor P.B. Rosar also mentioned about this Doppler dilemma in a different way. So for example, as long you have to fix your R maximum, that is up to what distance you want the data. So based on that, you will fix some PI. It depends on your pulse repetition frequency. You fix some pulse repetition frequency, and you will get R max. But if the cloud is within this R max, then you don't have any issue. But then if there is a strong precipitation beyond R max, then what happens? What happens is, you can see it in this picture. So the pulse is going, and then the echo is coming from here. but by the time you have sent the second pulse also. So you don't know exactly this, whatever this cloud your information you are getting, is it coming from the first pulse or from the second pulse? So that is the problem that you face here. So for example, in this case, you can see when you are fixing R max at 120 kilometer, you see these echoes. These echoes you can see here, but they are not the real echoes. These actually they are not at this range from the radar. Similarly, if you put a 250 kilometer maximum Rmax, you will get these echoes. These are also not real echoes because these are at some other distance. You can see here, within this distance, if you have a 500 kilometer range, actually they are beyond this 250 kilometer. But because of this this range folding, actually they are coming inside the this one. So this is what this problem comes. Actually, then you have to see that actually you have to use a different kind of a PRF. If you use a 500 kilometer PRF, but the problem is if you put a small PRF, so you'll get a long range. Rmax will be large, but then the problem is your V maximum, velocity maximum also reduces. So then what happens? The velocity folding occurs here. So instead of it is supposed to be like this. If you make a 360-degree 360 azimuth, the velocity field will look like this. But then if you use a smaller PRF, then instead of going like this, it will fold here, and then there will be ambiguity. Suddenly you can see in this picture, in this light color, suddenly you see a dark color here, and similarly in this dark color, suddenly you see a light color here. So this kind of velocity folding occurs. So this is what we call as the Doppler dilemma. So what to use? What is the best PRF to use to get rid of these two things? One is you have a range problem, you have a velocity problem. So you should have some sort of a bargain. So what kind of PRF you have to use? Otherwise, if you have the other way of getting rid of this problem is use a dual PRF technique. So this is what normally people use to get rid of this dual this problem, so that we can resolve these issues with the dual PRF technique. Okay, so there are several error sources for weather radar observations. This is actually a WMO slide. So you can see you have so many things. I have already described a few. There are so many described, so you should know these things when you are using weather radar. Particularly if you have this kind of some blockages, you don't get any information beyond that blockage. And then you do get sometimes, apart from the weather echoes, you can get echoes from the birds, you can get echoes from the sometimes from insects. So sometimes you get anomalous propagation. Sometimes you overshoot the clouds. So several other problems are also there. We should know all these problems actually when you interpret the weather radar. Then in addition to that, there are some other problems related to the radome. Because when normally you put the antenna is covered with a radome, because many times actually what happens is antenna is a parabolic dish. Most of the time we use parabolic dishes. So particularly when you use when the wind is very strong, it will put a lot of wind load on the antenna, and then sometimes antenna will be blown away by the wind. So to avoid those situations, actually we put radomes around that to protect the antenna and other electronics inside. But then normally these radomes are transparent to these radio microwave frequencies. But sometimes from the joints you get some discontinuous echoes. So all these things we need to consider. And also these sometimes water stays back on the radome. When radome is not cleaned properly, or when it's dirt, then there will be some water will remain there, and then that can cause some attenuation of your microwave. So we need to consider all these things. In addition to the technical, the practical problem, there are other geophysical problems. when you're using a single polarization radar, so you're maybe transmitting only horizontal wavelength. But then if you see the raindrop is not spherical all the time. When the drop is small, then it is spherical in nature. But then if the drop size increases, it becomes a spheroid like this. Then what happens if you use a horizontal wavelength? Then you will get a very strong backscatter because of your increased cross section. So, but it is actually much more than the equivalent sphere will give. So you will overestimate the rainfall. So this is the problem with the single frequency radars. And then another problem is actually the conversion of reflectivity into rain rate. So maybe I'll show one slide what are the problems here. So in the nature, normally all drops are not spherical. So you see the ice particles having different shapes, and then drop sizes are actually the size, the shape also differs from its. It's not a spherical shape. It actually you see kind of a different shape, and then because of that there will be an overestimation of rainfall, particularly if you're using only one polarization. And there is another source of error is actually the ZR relation, because these kind of radars will provide only the reflectivity for rainfall estimation. So when you have only reflectivity, you have to convert that reflectivity into rainfall using a priori relation or known relation, the so-called ZR relation. From the reflectivity, using that relation, you can convert that into the rainfall rate. But then this ZR relation is not a unique relation. So you can see this is mainly because it relies on the measurement of one. It is mainly because the reflectivity and rainfall rate, the dependency on the drop size is different. So the rainfall rate, the reflectivity Z is proportional to d to the power of 6, and whereas the rainfall is actually something like d to the power of 3.67. So the dependency is different. So if the drop size changes, both these parameters vary differently. So that is the problem. That is why you don't get a unique relation, ZR relation. So, and it varies from one type of rain to the other type of rain, one region to the other region, one season to the other season. All sorts of variabilities are there. And that's why actually this picture is taken from Batten in 1973. By then actually you see how many relations are given. Yes. So it is not a unique relation. So that is the reason why you get a lot of error actually if you use a particular relation. And this is actually, you can see this, the reflective to rain rate. For one type of rain, you will get these red dots are for one type of rain, and then blue dots are for one other type of rain. One is for the tropical and another one continental. So this is completely different at different frequencies. So in the US also, they use a different ZR relations to convert reflectivity into rainfall. For convective rain, they use one relation. For tropical regions, they use another relation. Stratiform rain, another relation. So, and then in Eastern USA, one relation, Western US, another relation. Even at in our region also, we see large variations in the DSD. From even in at one region, from season to season, you see large variations. The ZR relation, the coefficients, or you can see how they are varying as a function of a month. So it's not unique. So we have to consider all these things. And then this is another source of error, because when the radio wave propagates into the atmosphere, then it will undergo attenuation by atmospheric gases, by clouds, and by rain. But atmospheric gas attenuation is very, very small for whatever frequencies normally we use for the Doppler weather radar applications. So we can neglect that. And then, but the cloud attenuation is also is small, but we can calculate that. But the rain attenuation is very, very high, particularly when you are using higher frequencies like expand radar. So So this needs to be considered actually for estimation of rainfall, because your power itself, you're using a power to the estimate, you're using the backscattered power to estimate the rainfall, and then rainfall it will itself attenuates your backscattered power. So this is a problem. So we need to properly correct it. So with a single frequency radar, it is very difficult to correct these things. So the solution is for some of these problems is that using the dual frequency, dual polarization radar. So dual polarization radar, if you have the advantage of the dual polarization radar is you transmit with one polarization, receive the polarization, or also with other opposite polarization. Somebody is raising hand, so they have any question? Hello. Hello.
Sir, please continue, sir. We can
You can
constant section.
yeah.
We can do it in last.
Okay. Because some signal came as it somebody is waved, raised their hand, so I think that's why I'm asking. Okay. So some of these problems can be rectified with the use of dual polarization radars. Dual polarization radar, you can transmit with one polarization, receive with the same polarization, also with opposite polarization, depending on what type of mode you are operating. But then you can get the information in with the two polarizations. So what is the advantage of having a dual polarization? You can get the improved estimation of rainfall. You can improve the rainfall estimations. You can detect the non-meteorological echoes, whether if the echo is a meteorological echo or like a rain is coming from the rainfall, or it's coming from the like insect or bird, or from the ground clutter or some other clutter. So you can detect those things. And also you can design different types of hydrometers, whether it is a solid hydrometer, is a liquid hydrometer, whether it's a heavy rain, hail, snow, sleet, whether it's a light rain. All these things we can design. We know that actually what type of hydrometer it is. And the other advantage is you can retrieve the raindrop size distribution with the dual polarization radar technique. So these are the additional advantages that normally you don't have with a single polarization radar. So what are the additional parameters that you can get with the polarimetric radar? With a single polarization radar, you are getting only the reflectivity, Doppler velocity, and spectral width. So with polarimetric radar, you get all these three parameters at two polarizations. And then so from there you can calculate the differential reflectivity. It is the ratio of horizontal to the vertical power return, ZHH by ZVV. So that gives actually information about the drop shape. So you can see here, if it is a oblate shape drop, then you will get the reflectivity greater than, ZDR greater than 1. So you will come to know that what kind of shape approximately, what is the shape of the raindrop. And then also we can also use, later I will show you how to estimate the raindrop size using this information ZDR. And then there is another parameter called correlation coefficient, it's called ρHV. From there you can actually identify what type of hydrometer it is. Is it a meteorological target or non-meteorological target, or is it a mixed type of hydrometer, or is it a liquid type? Then other is linear depolarization ratio. You transmit with one polarization, receive with two polarization, then from there you can calculate the linear depolarization ratio. So it is also a good indicator of mixture of precipitation types. So these are all the polarimetric parameters from the scattering point of view. From the whatever the scattered echo, whatever you are getting from there, you can calculate. Similarly, from the propagation also we can get some parameters. See when a radio wave propagates into the atmosphere, when you are using two polarizations, particularly when the drops are, if the drops are spherical, you don't see any big change in the propagation of the two waves, horizontal and the vertically polarized waves. But if the drops are like the oblate shape, then the horizontal polarized wave will travel in the water drop for longer time, so it will slow down compared to the vertically polarized wave. So and because of that, there you see a change in the the propagation. Okay, so that propagation change normally you see in this one is called phi dp. This two-way differential phase. What you get it from different ranges. This phi dp is a very important parameter. So from the range derivative of phi dp, you get a parameter called kdp. So this is the very important parameter in polarimetric radar. So using this parameter, we derive. In fact, we do several things. We correct the attenuation in the reflectivity using this KDP, and also we can directly derive rainfall rate from the KDP. So KDP is a very important parameter because the KDP is directly related to the liquid water content. So or otherwise you can say rainfall rate. So because the dependency of KDP and then rainfall or liquid water content is similar on the raindrop size. So even the raindrop size changes also because these two parameters vary in a similar way. So the relation won't change drastically. Whereas the Jada relation changes drastically with the change of raindrop size distribution. So that is the advantage of the KDP. And then of course KDP, particularly when you're using a radars like X-band radars, the KDP value will be very large compared to the S-band radars for the same type of precipitation. So we can use the KDP from the KDP, whatever information we can get the KDP, the attenuation we can calculate, and then from the attenuation we can correct for the attenuation, the reflectivity, whatever attenuation is undergone by the reflectivity factor attenuation we can correct using the KDP information. So and then also we can use directly KDP to calculate the rainfall rate. So these are some of the, this is how we can calculate rainfall rate with the polarimetric radars. So with a single polarization radar, we have only the one parameter, the reflectivity factor. So from there we have to convert using some known from ZR relations. We have to convert into the rainfall rate. But whereas here you have several parameters at your disposal to calculate the rainfall rate. For example, we can use a traditional ZR relation. We can use KDPR relation. We can use multi-parameters. We can combine KDP, ZR, or several ways you can combine. Several parameters are there with you, which we can use for calculate the rainfall rate. So now we have another problem. In a single polarization, you have only one parameter. You have to convert into rain rate. But here you have several parameters. Which one I have to use? So people have tested different relations, and you can see here with a simple ZR relation, and then here is a multi-parameter relation, and then this is the bias. If you use a polarimetric radar, so the bias is very close to 0, and RMS is also very small here. Whereas if you use the conventional radar with the ZR relation, you can see the bias itself is very large and the RMS is also large. And here also you can see another example with the rain gauge network, very dense rain gauge network. When they compare, the operational radar actually overestimates the rainfall compared to the actual the rainfall, whereas the multi-parameter relation is giving a better result. So it all shows that the polarimetric radar provides improved rainfall estimate. That is the one important point we have to remember. So that is one important main advantage of the polarimetric radar. And of course, which parameter, which relation we have to use, there are people are using different ways. They are suggesting that you use a hybrid polarimetric rainfall estimator. If the rainfall, if reflectivity is less than this, use this relation, that relation, like that. There is a kind of a trees they will build. Using that, those kind of trees, decision-making trees, we can calculate, we can use different types of parameters to calculate the rainfall rate. So that is one important advantage with a polarimetric radar. The other one is actually you can get the raindrop size distribution. See, for example, raindrop size distribution, there are several models are there to explain the raindrop size distribution or to describe the raindrop size distribution. Some people describe it with a exponential distribution, some people with gamma distribution, some people use with log normal distribution. But whatever distribution you use, you can use those distributions, and you can calculate, you can directly retrieve the drop size distribution with the polarimetric radar. So for example, you see, if you assume raindrop size distribution follows an exponential distribution like this, then what you want is actually, you wanted to calculate the dm, because ultimately you want to know what is n naught, what is lambda, so that for a particular d we can calculate the nd. So how do you calculate m naught and then lambda? So the lambda can be calculated once you know the dm. So this dm is estimated from the differential reflectivity here. Differential reflectivity we can get directly from the radar. So using an empirical relation between the dm and then zdr, and then you can calculate the lambda. And once you have this parameter, you can also calculate m naught. So that way you can calculate the total raindrop size distribution using the exponential method. But the problem is, if for example, if you wanted to consider it as a exponential method, is not exponential method, exponential distribution is not explaining all the variability in the raindrop size distribution, and then I wanted to assume it as a gamma distribution, then you need, gamma distribution is the 3-parameter model. So you need 3 independent parameters from the radar to calculate the 3 parameters of the gamma distribution. But since 3 independent parameters are not there, so they use a constrained relation between mu and lambda, and then using this constrained relation, they make it the total relation into a 2-parameter relation, and then again they calculate the parameters and all 3 parameters of the distribution. So and then there is another method to calculate the DSD. It's called beta method. So instead of assuming that raindrop size and shape follows a particular relation, they take it as a this coefficient as a variable like beta. So using this and then using all other radar parameters, we can calculate the raindrop size distribution using this one. So this is directly we can calculate, we can retrieve the raindrop size distribution, and also we can get the microphysical process, like these several processes I have listed here inside happening the cloud at different heights of the cloud. So we get, these are the different microphysical processes, and by looking at the these parameters, whether they are increasing or decreasing or remaining constant. So these parameters actually contain they're actually in their imprints of microphysical process. By looking at these parameters, we can say what kind of physical process is occurring inside the cloud. Okay, so if for example, if evaporation is occurring, then obviously the drop size will decrease. When the drop size decreases, the reflectivity factor will decrease. Similarly, when a collision coalescence occurs, the particle size increase. The particle size increase, the reflectivity increases, and when they like that, several things we can calculate. We can guess by looking at the polarimetric products. Okay, so the second important advantage of having a polarimetric radar is either we can derive the drop size distribution, or by studying that variation of drop size distribution, we can get the microphysical properties, or by directly looking at the polarimetric products, the variation of polarimetric products, we can get the microphysical process. So it means that the second important point is we get the information about the microphysics of precipitation if you have a polarimetric radar. The first one is improved rainfall estimate. The second one is the improved the information about the microphysical process. And then the other important information that we can get with a polarimetric radar is we can classify what type of hydrometer it is. Is it a solid hydrometer? Is it a hail, or is it a grapple, or it is a rain, or is it a light rain, or is it even an insect? So these kind of things we can identify using the hydrometer classification. Pardon? Hello. Yeah. So there are different hydrometer classification schemes are available. Some of them are supervised, some are unsupervised, and some are semi-supervised. So actually it all started with the Boolean type of classification schemes. Then they used to fix that if the reflectivity is more than this much and ZDR is more than this much, then it is this type of hydrometer, like that in early 90s when the polarimetric radars were available. So these kind of Boolean type of hydrometer classifications actually are not unique. So sometimes you will have the same conditions are satisfying for other type of hydrometry also. So then that's why then people now slowly switched over to the fuzzy logic based hydrometer classification schemes. For example, you can see here, these are the original tables. They used to have these kind of tables to identify what type of hydrometers. But now I think people are all are using these kind of a fuzzy logic based systems. So in the fuzzy logic, because you feed all these parameters and then you know the properties of these things, and then based on that you put a use a known membership function, and then you give the scores to all these parameters based on that membership function, and then finally calculate the score for each of these parameters. So then you will get what type of hydrometer it is. So this is one example showing that identification of different types of hydrometers here. So starting from rain, hail, mixture, then heavy rain, big drops, grapple, crystals, all different types, where exactly they are located in, within the radar volume. So all these things can be estimated or can be retrieved with having a polarimetric radar. So this is another important advantage. So three major advantages is, one is improved estimation of rainfall. Then the second is the information of getting information about the microphysics of precipitation. The third is the identification, hydrometer classification. I will skip this for time being. So this is the present existing network of radars we have in India, IMD radars here. I just took this slide from IMD, and this is their planned network in future. I think very soon, I think this network is going to be realized. This kind of radars are available in the country now, will be available in the country in near future. But you don't have any information about rainfall over the oceans and then some other regions. So the only way of getting that information is actually through using satellites. So this TRMM, I just introduced only a few. I have a few slides on the space-borne radars. I will show those these things, and then I will take up the questions. So the TRMM is the first space-borne radar dedicated for the precipitation. You can see that I have some videos I just downloaded from to show that here. This is the first space-borne radar. Actually, normally you get these kind of pictures. In the background, you have the infrared picture, and then you have a TMI picture, microwave imager picture, and then with the radar, what you get is the vertical distribution of precipitation. So if you have only a microwave imager and infrared, so you get this kind of background and this kind of picture, color picture. But then if you have a radar, you get this kind of a vertical distribution. So what TRMM has provided is actually provided actually that's why the people calling it as a moving rain gauge. It has given the first glimpse of global precipitation rain rates. So you can see where exactly the high intense rainfall regions, and then where you see the dry regions. So it is a highly successful mission. It served the researchers and then the community for 16 years, nearly 16 years. It has provided wonderful science. So for example, with the in addition to this global tropical rainfall, and then we can see here actually we can divide actually what type of precipitating systems are there in the country, whether they are actually the shallow rain regions, where is the shallow rain regions in India, and then where are the deep convective regions, and where are the deep wide convective regions, where are the stratiform dominated regions. So this kind of information we got actually because of the this TRMM. And also we got the vertical structure, how extent, how high these clouds can go up. So you can see in the northwest India, the clouds you can see up to the maximum extent of 20 kilometer sometimes. And then this is the vertical structure, you can see clearly. Actually, in some of the regions, you see the broadband structure, and in some of the regions completely absent. So this indicates that this region is convectively dominated region, and then whereas in other regions, regions like these, you see a clear broadband structure, and then it indicates that there are stratiform dominated regions. And there are regions where you see maximum rain here at lower altitudes like Arabian Sea. So it indicates that this is actually the shallow rain is predominant in that region. So these kind of information, I think it was not there earlier when TRMM has provided this kind of information. And also by looking at the ISO lines, we can also get some information about the microphysical process occurring in that region. For example, if they are actually like that, if these lines are increased, they actually as it comes down, as you come down, the reflectivity lines are actually moving towards the higher reflectivities, indicates that there is a hydrometer growth is occurring at lower heights. So whereas here it is, you see here the opposite is happening. So that hydrometer decay is happening here. So that means that the evaporation is predominant in these regions, and then the collision coalescence growth is predominant in these regions at lower heights. So, but then TRIM, after the success of the TRIM, then people have wanted to extend the region as well as the capability of in both ways, both in region. So they wanted from a tropical region, they wanted to get information even up to 70 degree north to some plus or minus 70 degree. And also they wanted to get the highly sensitive echoes, even the reflectivity is lower reflectivity is also they wanted to get. That means they wanted to study even the light rain. So what they did is, instead of one radar, they have kept two radars in the two precipitation radars in the satellite. On the satellite, this is how it looks like. So they have two radars. So one radar is operates at a Ka band, is a 35 gigahertz radar. Other radar operates at Ku band like TRMM. So this Ku band, the combination. So this is a Ka band radar. Its swath is limited. Ku band swath is slightly larger compared to the Ka band. So the advantage, and this is of course GMI, the microwave imager, which is having much wider swath. So what you are getting here is that information about the information about the precipitation with the three sensors. One is the GMI, which gives the horizontal distribution of the rainfall. And then KU, KAPR also gives the horizontal distribution, but also they give vertical distribution of the precipitation. By combining KU, KA radars, I think we with the two radars, we can get the even the raindrop size distribution also. So that microphysical information also we are getting directly from the satellite information. So the another concept of GPM is actually they have one core satellite like this with KU, KA band and GMI. And also they have several microwave imagers. So what they do is all this information, microwave information, they actually combine all this information, and they wanted to get global maps of precipitation every 3 hours. In fact, you can see here, these are all several microwave imagers, including ours. So you can see that if in 3 hours they have complete information about the complete global precipitation information using a constellation of several microwave imagers and a core radar. So as I said, that because the advantage of having two radars is actually we can get we can derive the raindrop size distribution using the two radars, and then you can see here where exactly within India, what is the drop size, where exactly the drops are bigger, where exactly the drops are smaller. So in the northwest India, and then these parts, here, these slopes of Himalayas, you can see the drops are slightly bigger, and then whereas central India, the drops are a little bit smaller compared to these regions. And then in the northern Arabian Sea, you see the smallest drop sizes. Of course, there even for the same rain rate, we expect the raindrops to be similar, but then because of these microphysical changes, the drops are different in different regions of India, different climatic regions of India. This is actually one type of constellation where you put all the radars and images in one satellite. Whereas here, there is another way of looking the systems by sending several satellites in chain, so that they pass the same region with a very few minutes gap, so that what we can do is we get the complete information about that system. This is one such system. This is you can see here there are several satellites passing within a gap of few minutes. So the advantage of having this chain is actually you get this kind of information with the same system you are seeing with the different satellites. So for example, this is the Calypso, is a LiDAR, so you get only the cloud top information, and then the very weak clouds, you can get that from the Calypso, whereas the CloudSat will provide you the vertical distribution of the rain region. But then it also doesn't give the completely all the rain region, because once it comes into the rain region, then the signal gets attenuated with the 94 gigahertz, and then other payloads will give you information, the horizontal extent of that information. So this is how the spaceborne radars are have evolved. It started with the TRMM, and then you have a GPM, and then also you have a CloudSat, and then what we are recently, the NASA has launched a experimental satellite called RainCube. It's a Ka-band radar. It's a very small radar. It's actually a few kilograms weight. So this is experimentally, they have successfully proven the technology. It has several technological advances they have made with this radar. So this is on a demonstration satellite. So, but then it is still operating for the last 1.5 years or 2 years. So it is the success of this mission actually has paved way to the future spaceborne radars. And EarthCare is actually is planned to be launched in 2022. It is also like a similar to the CloudSat, but having advantage of Doppler capability. So in the future planned spaceborne radars, actually now people, in addition to the measuring the rainfall, vertical distribution, and all these things, they are planning to now see how to understand the processes occurring inside the clouds. So then all the future spaceborne radars, they are planning actually to understand the process in addition to the measuring. So all these planned missions are all like for understanding some process. Okay, so then instead of sending only one radar, they are actually now thinking of sending several radars in multi-frequency radars. In fact, they have plans to send 3 cloud profiling radars, like one Ku, Ka, and one W band. Okay, and then Japan is also planning to have a GPM 2. So several radars are being planned in future. And also it comes to the ground-based radars. Actually, now people are using different pulse compression techniques to, people now are slowly moving to the solid-state devices from the tube-based magnetron and other things. So then they're going for the advanced pulse compression techniques to get the high range. So this is actually is not really an emerging technology. I think now this technology has emerged successfully. I think now many radars actually are using this technology. And then, the one which is actually challenging is phased array antennas. So phased array antenna technology is now an emerging technology in India. Actually, outside, actually, it started in 2003 itself in US and other places. Actually, they have some radars, phased array radars, but none of these phased array radars, they are still in operational, they are still in the research mode. None of the phased array radars are in the operational stage. So these radars actually we have to take up, and there's a lot of scope for the development of phased array radars. Because these kind of radars will provide a lot of flexibility, so you can study the very fastly evolving or rapidly evolving systems like thunderstorms, and then even tornadoes we can study. Because the traditional radars normally take something like 5 to 10 minutes to complete one volume scan, whereas the phased array radars will take only hardly a minute to complete one volume scan. So this kind of a fast scanning you can do with phased array radars. And of course, actually, with the polarization radars, we can have improved understanding on microphysical process, and then how to convert this knowledge for the usage in forecasting systems. That is one thing which is actually very challenging. And the other, I have a feeling that there is a disconnect between radar meteorologists, hydrologists, and numerical weather prediction communities, particularly in the use of polarimetric products. So the polarimetric radar products are several products are being given, but then the utilization of these products in the numerical weather prediction schemes is a very big challenge. So that needs to be addressed. That is one of the challenge I think we have to address, and then there's a lot of scope for research in that direction. Thank you very much.
Thank you, sir, for the informative talk on radar fundamentals, like the different types of Doppler weather radars, their basic components, applications, limitations, and also how we can overcome the limitation using polarimetric radars, and also sir talk about the future radar plans also. Thank you, sir.
Thank you, sir.
So now the session is open for all. So the participants can put questions on chat. Sir, I have a few questions.
Yeah.
So Dr. Meera was asking that which tool is used to draw precipitation measures?
Precipitation?
Measures.
Precipitation measurements.
Yeah.
Which
So
tool
possibly, Dr. Rao, it is some maybe isolines of precipitation, something like that.
Oh,
Isolines.
isolines. Okay, isolines of precipitation. Okay, so that is actually the whatever I have shown there is the reflectivity isolines. I think that's what the question is.
Sir, one more next question, Dr.
No.
Prakash.
Just a moment. I think that is the reflectivity isolines. We are talking about one reflectivity factor, reflectivity factor Z, and then that line, that for example 35 dBz. That 35 dBz, how it is varying with altitude. That line. So that whether it is increasing or decreasing, based on that we can infer some microphysical process. I think that's what she means. Okay.
Okay, sir. So Dr. Prigasam was asking, in which way you are giving approval for launching the space vehicles?
I am not giving any approvals for launching space vehicles. These are the global satellites. So he wants to know about these satellites. So
no,
we are
sir.
not giving any approval, I think, but these are the future space. These are existing and also future spaceborne radars. So these things are evolved after the discussion with consultation with all the countries, and then some people are taking lead in that. And of course, these are all not Indian satellites. These TRIM and GPM are Indo-US satellites, and then RainCube is a completely a US satellite.
Okay, sir.
And
So,
Earthcare is a European satellite.
okay, sir. So, sir, Meenu R. Nair was asking, how can we get drop size distribution from wind profilers? Is it derived from zeroth moment received power?
It is basically the spectra, whatever you get from that spectra, once you correct it for the velocity and also the turbulence. Okay, because those particles, the raindrops are actually getting modulated by the turbulence also. So if we can deconvolve the spectra and correct it for the velocity, then the whatever spectrum you are getting, that can be correctly converted into the raindrop size distribution. So what you have to do, two things. One is you have to deconvolve the spectra for turbulence, and the other one is you have to correct it for the vertical wind.
Okay, sir. Sir, Swati Chauhan was asking how to deal with the NaN values when converting polar coordinate system into Cartesian or weather radar data.
I think you are asking this question to the wrong person. Anyway, I think that's not a big question. Big thing. You can do that. I don't know which software you are using to convert that in NaN values into. Okay.
Okay, sir. The Praveen was asking, did you mention that we can estimate drop size and shape distribution using dual polarized radar?
Yeah. Drop size information, raindrop size distribution information we can get with polarimetric radars. Yes, that's what I have shown.
Yes.
There are different ways of getting the raindrop size distribution with polarimetric radars. If you assume exponential method or the gamma distribution, if you assume it follows the gamma distribution also, still you can get the raindrop size distribution. Yes, we can get that.
Sir, he has one more question about the estimation of the drop size distribution with two radars. Can you please elaborate the working principle on which it is based? Is it possible to that with a single radar but operating on multi-frequency?
I think he is asking about this one. Actually, in this one, we have two radars, two frequencies rather. One is actually, even with one radar we can get this info. We can derive the raindrop size distribution information. But only thing is, like I told, we have two things we have to do. One is we have to deconvolve the spectra for turbulence. Other one is we have to shift. We have to get the vertical velocity. So if you have the vertical velocity, like for example, if you have MST radar type of radar, MST radar, this is the MST spectrum. You can see the solid line is the MST spectra. You are getting two echoes. So this is the one which is actually having the clear air information. So this gives the information about the turbulence. This gives the information about the vertical wind. So using this information, we can you can correct this spectra, and then that spectra you can use it to convert. You can convert the spectra after correction to raindrop size distribution.
Okay, sir. So Daniel Simon was asking, there is a bright band centered at the mid-tropospheric level in the radar reflectivity diagram shown. Is it because of the freezing of water particles at that level?
Yeah. When convection occurs, it throws a lot of small hydrometeors into the upper heights, and then when they fall in the trailing regions. So when these trailing regions, when the ice crystals slowly grow, initially by the vapor deposition, and then when it comes close to the 0 degree level, because at higher heights it is only minus temperatures, and when it comes to 0 degree, then what happens? The ice particles become sticky. If you just like I always give this example, even if you open the refrigerator and then just after some time, if you touch the ice, it is sticky because the outer layer starts melting. So in the same way, around 0 degree isotherm level, the ice particles become sticky, and then when they collide each other, they stick together. It's called aggregation. So once it crosses 0 degree, then outer layer of that big aggregated particle starts melting. So then for a radar, it looks like a big water drop. And radar gets backscatter mainly from the size. The Rayleigh scattering depends on the drop size. Basically, the bigger the drop, then you will get a strong backscatter. So you get a very strong backscatter from that region. That is one factor. Other factor is the change in the dielectric factor. The dielectric factor for ice is actually 5 times smaller than that of water. So because of these two main important factors, actually you get a strong backscatter from that region. But once that big aggregated particle melts, it becomes a small, then again you will get the actual backscatter at lower heights. Only near close to 0 degree isotherm level, you get a strong backscatter. That is what we call the radar breadband.
Okay, sir. He has one more question. In case of space-borne radars or lidars, do they provide gridded products? So, if so, what is the maximum resolution in time and space which they provide?
Yeah, the space-borne radars actually they give only the profiles. But then now the rainfall information, what they are now doing is these spaceborne radars are mostly these are all low inclination satellites. So when they come, then they measure, then they go. But actually what they are doing now is they are merging several satellite data sets they're combining different satellite data sets, infrared, microwave, radars, all these things they are combining, and they are giving these products. So several such products are available, gridded products. and they are available now. The like iMerge. iMerge is giving it, I think, half an hour resolution, and then with every 0.1 degree by 0.1 degree, and there are different data sets like GSMap, iMerge, CMORPH. Several data sets are available. They are all giving at very high resolution, temporal resolution, like half an hour to 1 hour temporal resolution, and then 0.1 degree resolution.
Okay, sir. So there is no more questions, sir.
Yeah,
Thank you, sir.
Yeah, thank you, Dr. Narendra. It was a very, very excellent talk. And
Thank you, sir.
considering that number of questions, I'm sure that it was well received also. Thank you.
Thank you very much, sir. Because I had to rush, I had to cover so many things in my presentation, starting from wind profilers to spaceborne radars. I once again thank you, sir, for.
Yeah, thanks a lot. No, we have to thank you. Yeah.
Okay.
Thank you, sir. It's a very informative, a very lengthy session also.